Hello everyone, welcome to Chemistry Chapter 3, Lecture 1. In this lecture, we're going to cover on your own problems 3.1 through 3.8 in the textbook. So you will need a periodic table for this lecture. You will need your note sheet and your textbook, and we are also going to use the calculator just a little bit. All right, so and in your book, the first problem that we're going to work is on page 73. And before I get started on the lecture, if this video helps you out, please consider buying me a coffee. You can find a link in the description box. You can use PayPal or Venmo. It's just $3. Or you can scan this QR code and it'll take you right to the Ko-fi page. All right, so let's take a look at your notes. We'll just talk through these a little bit. As far as the continuous and discontinuous theory of matter, the author just goes through what scientific thinking was about matter throughout the last several hundred years. Even going all the way back to Greek times. So just read over that on page 69, and so that you know basically where it's coming from, but not really important in terms of the kind of problems that we're going to be working. The law of mass conservation. All right, so we had in the last chapter, first law of thermodynamics. The law of mass conservation is matter cannot be created or destroyed. It can only change form. So a mathematical way to think about that is that mass before a chemical reaction or a change has to equal mass after. All right, maybe it changed forms. Maybe it changed from solid to a liquid to a gas, whatever, but mass before has to equal mass after. So let's take a look on page 73 of On Your Own Problem 3.1. It says, in a careful experiment, a chemist burns 15.4 kilograms of wood in a fireplace. The chemist collects all of the substances produced by the fire. He measures the mass of ash produced to be 925 grams, the mass of carbon dioxide produced to be 15.14 kilograms, and the mass of water produced to be 3.12 kilograms. How much oxygen was used up by the wood while it burned? Okay, so you haven't really necessarily learned all of the compound formulas yet, so I'm just going to write all this out. Okay, we'll get to those formulas soon enough. So what we've got is, if we want to write this like a chemical reaction, wood plus oxygen, and because we have the law of mass conservation, that has to equal the ash. So after the burning, we collected some ash, some carbon dioxide, and some water. So believe it or not, when you burn something, you make water vapor. Okay, and now we can fill in the numbers. We had 15.4 kilograms of wood. Oxygen we don't know, so I'm just going to make that X. For ash, it was 925 grams. If we convert that to kilograms, you can do that like we did in Chapter 1. It would be 0.925 kilograms. We do need to keep the units the same. And then carbon dioxide was 15.14 kilograms. And for water, 3.12 kilograms. Okay, so this is just an equation we're going to solve for x. So we'll get rid of the units for just a second. 15.4 plus x is equal to, and on the right side, we'd have 0.925 plus 15.14 plus 3.12. So that's 19.185. So we're going to subtract 15.4 from both sides. And we have x is equal to, and subtract 15.4. So x is equal to 3.785 kilograms of oxygen. All right, so that demonstrates the law of conservation of mass. All right, great. Well, let's keep going through the notes here. The next concept is the concept of the element. And an element is any substance that cannot be decomposed into less massive substances. All right, so for example, water versus oxygen, H2O can be decomposed. All right. However, oxygen, an oxygen atom, just the element by itself, yes, it's made up of protons, neutrons, and electrons, but that oxygen atom can't be decomposed. All right, let's do a general overview of the periodic table. I will say some of these, since these notes were published many years ago, a few of these things have changed. They're not a big deal. But on the periodic table, and I believe we're up a couple of elements higher than 118 now. 118 named elements. It may be 119, 120. I believe the most recent elements named tennessine. Those are elements created in the lab. Those elements with the large atomic number there. Really don't have to worry about those too much in this class. 92 elements appear in nature, so that part is important. And the remaining are manufactured in labs. The element symbol is the first or first two letters of the English or the Latin name. The jagged line separates metals from nonmetals, and the exception is hydrogen. So the jagged line we're talking about is this thick line here that starts up here at boron. I know you've had a few element quizzes by now, so you'll know some of these elements. To the right are not metals, to the right of that line, and hydrogen. Hydrogen is not a metal. And everything to the left, with the exception of hydrogen, to the left, those are all metals. All these at the bottom are all metals. All right. So, in your classroom, you may have color-coded. I think some of them are color-coded red, which means that they are a gas at room temperature, and they may be color-coded blue, which means they are a liquid at room temperature, and then everything else is black, meaning it's a solid at room temperature. All right. Elements bordering the line are called metalloids. That means they have properties of both metals and nonmetals. All right, metals are malleable. They have luster, which means they're just shiny, and they conduct electricity. Nonmetals are brittle. They have a dull appearance. They're poor electrical conductors. And then metalloids have properties of both metals and nonmetals. And some of them are good semiconductors. All right, so when we're talking metalloids, we're talking antimony, tellurium, arsenic, germanium, silicon, that's the most famous semiconductor. Aluminum, we typically think of that as a metal, but it is on the line. Boron would also be a metalloid. Okay, so let's take a look at On Your Own 3.2. So we're on page 77. let me bring that into view here. So which of the following elements are metals? So we have oxygen, magnesium, iodine, indium, osmium, radon, and hydrogen. So the ones that are to the left of the line are magnesium, indium, and osmium. All right, so you can find those on the periodic table yourself. That'd be a good exercise. But magnesium, indium, and osmium. All right. So if you want to make a wire for an electrical system and you only have the following elements to work with, which would you choose? Well, metals are good conductors of electricity. So of those three, the only metal is nickel. So nickel is to the left of that bold, jagged line. So nickel would be a good electrical conductor. And then 3.4. We have which of the following would you expect to break when it's bent? So nonmetals are brittle. Rhodium is a metal. Barium is a metal. But phosphorus is not. Phosphorus is to the right of the thick line. So we would expect phosphorus to break when it is bent. All right, great. Okay, so we'll clean off the board here and turn over to the next page in your notes. So compounds are substances that can be decomposed. So into elements by chemical means. All right, so for example, if you have water, we can decompose that water into hydrogen and oxygen. So that makes water a compound. Hydrogen appears in nature as H2, oxygen as O2. You'll learn about that in a future chapter. All right, so, and just a little bit of foreshadowing here, we also have to balance. All right, so this is a compound, but both of these are elements. All right, so really that's a hydrogen and an oxygen molecule there. All right, the next is the law of definite proportions. Okay, so we're about to do a little math of this. That's the proportion of elements in any compound is always the same. Okay, so what that means is for water, so keep coming back to water because I know you guys know the formula of that, even if you've never had a chemistry class. Water, H2O, is always 2 hydrogens and 1 oxygen. It's always that. So there's always that definite proportion. Excuse me. It's never H1.5O. Or water, you know, H3O is not water. It's always 2 hydrogens, 1 oxygen. Okay? So that's the law of definite proportions. Now, we can demonstrate the law of definite proportions through what I would call a recipe problem. And you'll need to memorize this procedure, okay? And so instead of reading through it, well, I'll just read through it real quick. If you get a recipe problem, we're going to determine the total mass of all the elements used in a trial run and disregard leftovers. We're going to solve for x in this equation. Trial run mass times x equals the total new mass desired. We're going to take the value of x, which is just a ratio, and multiply it by the mass of each individual element in step 1 to determine the new mass of each element needed. And then to make sure the mass of the elements determined in step 3 add up to the total mass needed for the new recipe. So let me demonstrate this on the next 2 problems. So on your own So you can read in the book a couple of examples with these problems on page 80 and 81. That'd be a good idea. Let's do on your own 3.5 on page 81. So it says when 12 grams of the element carbon react with 4 grams of the element hydrogen, which is natural gas, the stuff you burn in a gas stove or gas furnace, is produced. There's no leftover carbon or hydrogen when these quantities are used. How much carbon and hydrogen would you need to make 100 grams of natural gas? Okay, so first of all, we want to figure out what is the total trial run mass. Okay, that's step one. Well, it's going to be 12 grams of carbon plus 4 grams of hydrogen. So that is 16 grams. So that's step one. All right, we figured that out. Step two, we're going to have an equation. So we take that total, 16 times x, and we set it equal to the 100. We want, if you look at the problem, you want to know how much of carbon and how much of hydrogen do we need to make 100 grams of natural gas. Okay, so we have 16x is equal to 100. We solve for x. X is equal to 100 over 16. Or if you put that in your calculator, you'll get 6.25. So now we've done step two. We've got our multiplier. Step three is where we determine how much carbon and how much hydrogen. So for carbon, let's just write a C. That's the element symbol for carbon. We're going to take what we used in the trial run, which is 12 grams. We multiply that by 6.25, our multiplier. So if you put that in your calculator, 12 times 6.25 is 75 grams. And then for hydrogen, we have 4 grams. Okay, that's from the problem, 4 grams. We're going to multiply it by 6.25, and that would be 25 grams of hydrogen. So that is our recipe. That is the answer. Now step 4 is we just want to check to see that it adds up to 100. So 75 plus 25 is 100 grams. All right, and so let's check. But the answer is 75 grams of carbon and 25 grams of hydrogen. All right, so that was a pretty simple one. Let's try another. And remember, in the practice problems, in step 1, you do disregard any leftovers. We weren't given any leftovers, but if you have leftovers, you just disregard those. It's only what got used up that is the total trial run mass. So it says a chemist, 3.6, next page, a chemist decomposes 30 grams of a purple powder into 13.6 grams of cobalt and an unmeasured amount of chlorine gas. The chemist uses the results of this experiment to help him determine the recipe for making this purple powder from its elements. He then decides to make a kilogram of it. How much cobalt and how much chlorine gas will he need? All right. So we're starting here, and we're on page 82. We have a purple powder. And we decompose that into cobalt plus chlorine gas. Okay, we start with that 30 grams of purple powder. Said that the cobalt was 13.6 grams. And then we don't know how much chlorine, but we can figure it out because of the law of mass conservation, these two have to add up. So chlorine, which has a symbol of Cl, is just going to be 30 minus 13.6, which is 16.4 grams. So we had to do a little step and figure out how much chlorine that we started with, because the cobalt and the chlorine have to add up to 30. All right, so step 1, the total trial run mass is 30 grams. That was given to us in the problem. Step 2, we have an equation, 30 times x, and we have to set that equal to the total mass desired. All right, our total mass desired is a kilogram, but we're in grams, so we set that equal to 1,000 grams. We're going to convert that kilograms to grams. So x is equal to 1,000 over 30, and that is going to be 33.333. Repeating, the further you go out, the better off you'll be here. So try to go at least 3 decimal places. All right, but it is repeating. All right, and then 3, the recipe, how much cobalt and how much chlorine. So cobalt has a symbol CO. We're going to get that by taking the original amount, 13.6 grams, and multiplying it by 33.333. And then we're going to do the same thing for chlorine. That's 16.4 grams. We're going to multiply it by 33.333. All right, 13.6 times 33.333, 453.33. And then we have 16.4 times 33.333. That's 546.661. We'll just go with 0.66. And that is, I'm sorry, so that is cobalt on the top and chlorine on the bottom. Now, if you add those two up, you come up with 999.99 grams total. That's step 4. That's close enough to 1,000. So we have a rounding error here because it doesn't exactly equal 1,000 because we didn't go 33.333 forever. All right, we needed to stop. So here's our answer. This is our recipe. So if you want to make 1,000 grams of this purple powder, you would need 453.33 grams of cobalt and 546.66 grams of chlorine. All right, so that's really the only math in this chapter. So let's go ahead and do just a little more. So Dalton's atomic theory on page 83. I'm not going to read this for you. You do need to know it potentially for the test in terms of answering a true, false, or multiple choice question. So just read over these 4 points and read over page 83, but there's no reason for me to read that to you. Molecules are more than one atom bound together to form a compound. So all compounds are composed of identical molecules. All right, so abbreviating and classifying compounds, a chemical symbol, an abbreviation for an atom. So for example, hydrogen is H. And a chemical formula is the number of atoms that make up a molecule. Number of each atom that makes up a molecule. All right, so what the periodic table is it's just filled with chemical symbols for each element. But it doesn't give you the molecules. Okay, so let's work 3.7 and 3.8 real quick. I don't think you'll find this to be very difficult. And this is on, flipping over, we're on page 87 for both of these. All right. right, so 3.7 says, give the formula for each of the following molecules. For A, we have a molecule that has 1 atom of sodium, 1 atom of chlorine. Okay, so that formula is going to be just NaCl. If it just has 1 atom, you don't have to write a number. The 1 is implied. Okay, part B says 6 carbon atoms, 12 hydrogen atoms, 6 oxygen atoms. So that's going to be C6. So that subscript tells you there's 6 atoms of carbon. H12. That subscript tells you there's 12 atoms of hydrogen. And O6. 12 atoms of oxygen. All right, and then part C, we have 2 sodium atoms, 1 carbon atom, 3 oxygen atoms. So that would be Na2. C, the carbon atom, we don't have to put a 1 there. And then O3. So that actually has a name, sodium carbonate. You will learn that in Chapter 9. You'll learn how to do that. This is also a famous molecule that you might have learned in biology class. What is that? I'll let you either you make a guess and then you look it up. All right, finally 3.8, also page 87, says how many of each atom exist in the following molecules. So for KMNO4, for potassium there's 1, for manganese there's 1, and then for oxygen we have 4. And then Na3, PO4, that's potassium permanganate is the name of that one. This would be sodium phosphate. Na3, we have 3 atoms of sodium, 1 atom of phosphorus, and again 4 atoms of oxygen. And then part C, rubidium chloride, we would have 1 atom of rubidium and 1 atom of chlorine. All right, and you'll start with the next lecture, you'll start learning how to name these compounds. Okay, your homework for this lecture, what goes with it, I don't assign review questions 1 and 2. Your teacher may, so if that's the case, please do those. But what I assigned was, when I taught the class, would be page 97, 3 through 7 for the review questions. And for the practice problems, page 98, I assigned 1 through 7. All right, that does it for Lecture 1, and there's only 2 lectures for Chapter 3. It's really a really short chapter. So I'll remind you again how you can support me in making these videos. Hopefully they're a help to you. And so let's do a little play out tune in the key of G, and have a great day.